Okay, hello everyone. Now it's 10 quarter to 11, so I think we're going to start this session very soon. So just wait for a few more people coming in. Yeah, 11. 11. Okay, so yeah, welcome to the part two of this AI session. So I hope you enjoy like the part one that we have yesterday. Still remembering me giving a talk. And today we are going to have like very amazing talk that we are going to go through in this session. And this session is chaired by my colleague Nick Nicholson and also by myself, Samson Poon. So yeah, we will have this 11 talk in this session, and then after that we will have a discussion time for all of you to ask questions for the speaker as well. So I think yeah, not waste more of our time. May I introduce our first speaker, Dan Hartley, to come to give us the first talk from the Natural History Museum, London. Thank you, Ben.
Questions. Good morning, everyone. And today I wanted to share with you one of the projects I've been involved with over the past few years, mining trait data from botanical literature. And I'm going to use this project as a kind of case study today, because while the project is very much about data, plants, and climate change, it's also a story about how our approaches to AI have been shifting and what that means for our community. So let me start with the trait data itself. I've been working closely with botanists at the Natural History Museum in London and climate change modelers at Glasgow University in Scotland. And trait data is crucial because it allows us to model how plants respond to climate change. Think of traits like leaf size, seed mass, plant height. These morphological traits strongly influence how species interact with their environment. They determine things like reproductive capacity, dispersal ability, establishment potential, and overall range size. And when we have this data for species, we can then predict how ecosystems will respond to changes in the environment. However, getting this data is tricky. We need accurate quantitative sources of information. And where they do exist, like the TRI database, they do not have extensive species coverage. But this data is captured in the literature. E-floras are a great source of data. Also, every published species has a taxonomic description containing this information, and a huge proportion of these are available in the Biodiversity Heritage Library. We just need to find them and then extract the data. So we built a workflow to do exactly this. And the first step in the workflow, locate these descriptions. For e-floras, it's simple, just scrape the data. BHL was a little trickier. So we search BHL for a species, retrieve the page and the OCR text, and then check that the page contains the trait terms that we're looking for. We then detect the taxonomic names in the page and then associate each name with sections of text in the page. We then use a binary text classifier for each section to identify the descriptions matching each species, matching the sections. And at the end of that, we have botanical descriptions belonging to the species on BHL and online floras. Once we have those descriptions, we want to extract the trait themselves. And our first approach used Spacey, a Python library for natural language processing, and using BERT-based transformer architectures. These models can parse sentences, lemmatize words, and help us isolate the relevant trait terms. But developing these models was very iterative. We focused first on a set around 300 UK peatland species, and every iteration of the model was checked by botanists, validating our past documents against the original BHL descriptions. For the trait detection themselves, the recognition process had multiple parts. For numeric parts, like leaf length or height, we trained a predictive model. For categorical traits like leaf shape or color, we used rule-based models, which examined the syntactic structure of the sentence to pull out the traits and the terms. And this combination produced the highest level of accuracy that we could find, rather than just that purely predictive model. And the results, after developing the model, we ran the pipeline for all angiosperm species. At the time, that was 342,625 accepted names. And that produced 706,000 or just above trait terms. And so that's a size rivaling the trait database, just mined from the literature. And one thing we noticed was the trait space has a very long tail. Some terms are extremely common, but others are rare, appearing only occasionally in descriptions. And the other limiting factor is actually finding the descriptions. Of the 342,000 species, only 59,000 had descriptions. So that's about 17%. That low coverage was mainly because we were just looking for English language texts. So we faced a huge challenge. Building transformer-based models for every language would be a huge effort, but passing syntax across multiple languages is technically difficult and time-consuming. But at the same time, large language models were emerging, and using them for data extraction is very attractive. And I just wanted to give a shout out now to Deadpool, who a couple of years ago dropped me, Vince, and others an email. And I think the text in that email was just like, wow, cool, have a look at this. And she was using ChatGPT to map some raw specimen data to Darwin Core. And it got us thinking and opened our eyes to the potential of LLMs to extract data and map it to data standards. And we had the same pivot point in this project. Rather than migrating our transformer-based models to accommodate these new languages, let's try LLMs. So we developed LLM prompts that can take text in any language and then output the traits. And this is a very common switch I've witnessed, and I'm sure you've all been aware of over the past few years, from moving from traditional NLP-based approaches to using generative AI to extract the data. But how do these two approaches compare? We're in a very fortunate position in that we already had a gold standard trait data set carefully developed with our botanical collaborators that was extracted using the transformer networks. And that was to test how well ChatGPT performed compared to our transformer models. And the results are interesting. I'm sorry, this is an old slide. I did have the metrics on the new version, but I'll just read them out. So we have a mean similarity of 0.72. So when ChatGPT produces a term that lines up with the truth data set, we have quite a strong overlap. We've got precision of 0.60. So about 60% of what ChatGPT suggests is correct. So there are a lot of traits coming through that are not correct. We have a recall of 0.71. So it finds roughly 3 in 10. So it finds about 71% of the true terms, meaning roughly 3 in 10 traits are missed. So these numbers are not that bad for a generative model, but if you're doing scientific information extraction, especially for data feeding directly into climate models, is not bad good enough. Missing traits mean missing signals about species climate sensitivity. But we developed these LLM-based pipelines in a matter of weeks. The transformer networks took many, many months of work. And my team would not have had time to develop a multilingual version, so that data would have stayed locked away in the literature. But the power of LLMs and speed of development is very attractive. And to give you a final example, we've been prototyping new ways of generating data from BHL using Mistral for OCRing the text, and then using LLMs to generate a knowledge graph from the literature. We're using Claude AI to identify people, taxon, localities, and institutions in the literature, and then it generates a Cypher query to insert these entities into a knowledge graph. Working with AWS, we created a prototype of this project in just 8 weeks. So that's OCRing, articalizing the journals, and generating a knowledge graph representation of two BHL journals, Novon and the Botanic Journal of Linnean Society. So these approaches to data extraction are incredibly efficient. But here again, you get a trade-off. We have about 90% accuracy in entity detection, and we're working to improve these with better token windows and RAG models to validate the LLM outputs. This is a project we hope to continue with the BHL team, so please watch this space. But in conclusion, LLMs are extremely seductive ways to transform how we're able to extract structured data from literature automatically. So I'm out of time. But these need to be balanced against the needs for scientific accuracy and scientific rigor. LLMs are changing so rapidly. They're not quite at the point where they can outperform traditional NLP models, but I have no doubt we'll reach that in the next few years. Yeah, few thank yous, team behind the project, and especially Krian Q, who has developed the new LLM-based approaches and the LLM BHL prototyping work. Thank you very much.
Thanks, Ben. That was an excellent talk. And it leads on really nicely to the next one, which is from my colleague, Kirian Karu. And he's going to talk about LLM-based transcription of botanical catalogues for digital access to special collections.
Can you hear me? Okay. Hello, my name is Dorian. I work with Nikki at Kew Gardens, and I'm going to talk about a project I've been working on for the past year or so. We've been working on a pipeline that uses large language models to transcribe information from botanical catalogs into a CSV format, so it's easier for digitization and curators to access that information rather than having to type it out. So a little bit of context. Kew has over 7 million specimens that have been collected over 170 years since its establishment. And each specimen record contains rich information such as the specimens, the taxonomy, the locality where it was found, when it was found, and even by who. But over the past few years, Kew has been digitizing this information, mainly the herbarium sheets, and we've had over 6.4 million specimens digitized as of the start of September 2025, which is great. There's still a lot more that's being digitized and hoping to be fully digitized by next year. However, within the 6.4 million specimens that have been digitized, most of them are herbarium sheets that are stored in physical photos, as you can see in the image, and they contain both the first specimens as well as the information such as the specimen, the metadata, collectibles, and everything. They're easy to read, so they have standardized workflows to be digitized. However, some of them, which are stored in folders, don't have this information or fabricated, so they're harder to read, they're harder to type out, or harder for OCR to, just transcribe it. However, something which is nice is that these information were written as catalogs in books, so we have access to them, so we can transcribe them instead of having to read them from the various sheets. So that's the aim of this project. So the aim of this project is to help curators and digitization team to get this information that is in the catalogs into a format that is helpful and easier to work with, rather than which is messy, as you would see in the catalog image right there. It's semi-structured, but that's going to take a lot of time to type out or copy into CSV format, which is easier for the curators. So, as I was saying, the catalogs, they are restricted from the standard workflows we currently have, as they have varying unstructured formats. So they come down to what I call a manual transcription model. Like they take a long time to type out. They are costly and they're slow. Sometimes there are errors, but they're very important because they contain unique historical scientific insights, such as field collector applications, early classification systems, and even specimens that are not on GBIF. So what's the solution? Or simple. Let's use large language models and OCR to create a pipeline. So the easiest way to say how the pipeline works is we take the input image of the catalog pages, we extract the text from them, we then chunk them so they are individual text blocks that can be then sent to the large language models to be transcribed into a format that we specify through a schema. This will then be outputted into a CSV format for the curators to work with. Sorry. Okay. So to go a bit in depth into yeah. So to go a bit in depth into how each step of the pipeline works. So the first step, okay, the first step takes, let's say, a folder of images that are basically images of each page. These can be double images, like the double page images, like in the example there, or they can be singular page images, which is highly recommended because easier and much more higher resolution, better as well for OCR. We use layout detection. So in this case, we use deep detection library to split the images into columns of text, which are then split further down to singular text columns and stored sequentially in a list, which is then sent to the OCR for pre-processing. So step 2, this is where text extraction takes place. Each column is then passed sequentially to the OCR model to extract the text from the image. And this text is then sent to the next step, which we'll talk about for chunking. We, by default, use the Tesseract OCR, but we also have support for large language models with visual reasoning like the Qwen 2.5, and I do highly recommend using large language models since they are better at recognizing historical fonts and text compared to the default ones we have in Tesseract OCR or Kraken OCR as well. And step 3. So this is the text processing and chunking bit where the text is processed to remove any common OCR artifacts that we identify. So these can be where the ACA might end with AE, so it might end with E instead of AE, like it should, or there might be numbers instead of letters. It shouldn't be like that. This text is then processed further into hierarchical format of chunks. So we have divisions that are defined by the user. So in the case of the catalog we used is dicodes and monocodes. We then take the text under these divisions and split them further by the family names, which is done using regular expressions. Then comes the hardest part that took months of work. Was to then split them further into smaller chunks to send to the large language models. Main problem was contextual blocks. So these were then split down by specific species names, and these species names were identified using the taxonomically library. The chunk texts are also stored further as text blocks of information. So each text block will contain like in the table there, will contain the division, the family name, the species, and everything under that species. This singular row will then be sent to the large language model for transcription, which will look a bit like this. So the large language model will take the user prompt, which is the user explaining how the information on the species should be handled and how it should be returned in a structural format. So this can be Darwin code, the user specifies under a didactic schema. We also, so didactic schema will be under the JSON schema as well. So it's a different form of information that will then send to the large language model with each row of information. This information will be returned in a JSON format, which will then be converted to a CSV format for the curators to work with. So how well does it work? A simple example will be this, which is the input versus the output. As you can see, the semi-structured text from the catalog has been transcribed into a much more easier and searchable format, which is a CSV. Each element has the information, and each duplicates or different folders are in different rows. So it's easier for the curators to have a look at that, find the folder, barcode it, send it through for database integration. In terms of metrics, I've used reference scores, so this is just preliminary testing on the Lightfoot catalog so far. And we've seen that the species and the family names have there's strong recognition for finding the species names and family names using the current models, which was the Quen 2.5. And the descriptions as well were excellent, and we were able to have the extracted them into a good format. Sorry, the time is really up. And yeah, we also had high word error rates and character error rates from the descriptions, but there's a baseline for further improvement using better prompts and better resolutions. And as I said, as I've been experienced, well, some challenges we faced was more resolution or these scatter images that affect the OCR output. And there are also some occasional isolations where the species names are misclassified as descriptions, or the description endings are misclassified as species, as you can see in the example. Strict use of prompting is very much needed for this, so that the output structure is followed. The current pipeline is strictly designed for the semi-structured botanical catalogs, but they can be expanded further for other fields of text as well. But curator validation is needed, since this is not a full-on tool, but an assistive tool. Thank you for listening. If you have any questions, please.
So next we have an online talk, and that is from Kit Lewis in the US, and she is going to talk about its longest title, multimodal AI algorithm for year-over-year forest change detection at SJER using neon lidar, hyperspectral, RGB, and GBIF mediated data. Can you play?
Hi, I'm Kit Lewis from NASA Double Space. That's from call the ecological observatory network. Today I'm going to talk about track multi-sensor encryption at the SJE website, and how that can be done integrating hyperspectral, RGB, and field data to map tree level changes. So, wouldn't it be awesome to just take pictures from space or airplanes and get these huge swaths of imagery and pick out each individual tree species from hydroponics and put that directly into GBIF and also track that year over year. So that's kind of what this project hopes to do. And that's because which if you're interested in check the struct that's being done in the AI session, but each data product tells us something valuable, but each carries its own uncertainty. So LiDAR gives us structure, hyperspectral gives us species and health, and RGB can help define green boundaries. So positions or timings down the line is also compelling. Is to let these sensors reinforce each other so that one sensor's precision offsets another's uncertainty. And this is to the fact that airborne sensors rely heavily on GPS and IMU positioning. Accuracy typically ranges a standard deviation of 1 to 3 meters and can sometimes drift over to 10 meters. At the first scale, not a big deal. Talking about individual trees versus monkey, is less than a meter. You're talking about an entirely different individual. Right? sensors, we can use data to detect structure in hyperspectral context to correct this drift and link the crowns over time. And essentially that would allow us to space and time so that the multi-year data can become a coherent full-picture view of the forest. So the data inputs for this would be OG imagery from EOP, used for individual tree crown delineation, to deep forest or an extension of deep forest by Ben Weinstein, hyperspectral imagery from Otis and G, which is also from the EOP, to provide spectral signatures for species identity and vegetation health, and pods for vertical structure and vitality plots for validation and training. What's awesome is there's a project that does this, which is, when we bring these together, the overlapping data creates checks and balances, so each sensor can confirm the other. And this confidence through innovation, so integrating sensors. Innovation is what turns uncertainty into information. Perspective of position health, confidence goes up. When RGB data confirms species identity, uncertainty shrinks even further. The next step is to quantify confidence and expand this approach to other neon sites. So future work, the thing that I'm working on right now, that we'll be working on soon, is creating these confidence, these digital uncertainty confidence scores. So ultimately, this pipeline wants to transform raw sensor data into machine learning diversity records that can directly feed into platforms that do both data core and this physical reality to a digital representation that can be tracked year over year. And since I do have a little bit more time, I wanted to show kind of why this is important. So just from looking at this imagery, so this is not RGB imagery, this is a little bit more fine scale. This is the spectral instrument. I'm doing an experiment to run Pacific retrievals, but you can see that there's a drift of where this row is. Images on the same projection, so it's not a projection issue. But that, like I said, isn't a big deal. Scale things, but when you want to track individuals year over year, it can become an issue. And so far, it's honestly one of the biggest obstacles to sensing actually identifying individuals instead of groups. So thank you so much for your time. I was happy to talk about this and tracking uncertainty and connecting, which is like my biggest passion. So feel free to reach out.
Thank you, Kate. And then the next talk we are conducting in-person talk from one of my colleagues, Ariana Salini James from the Natural History Museum, London.
Hello. Okay, let me move this down so you can hear me. Okay, awesome. So yeah, thank you for having me here, although I do co-organize this session, so I might be a little bit biased. So I'm going to talk about AI-assisted quality text for herbarium sheet digitization. I'm going to hope that the microphone doesn't fall off. Maybe a little. Thank you. Oh, okay. Seems to. Hello. Okay. But I can hold it. Sorry, guys. It's the difficulties of being very small. Yeah, that's good. Hello? Okay, awesome. Okay, so just to give a little bit of background first. So I'm sure you guys were here for Samson's talk yesterday. Hopefully, yes, awesome. So Samson talked about this program that we had recently at the Natural History Museum, and that involved going to, doing mini projects with related institutions across the UK. I won't talk too much about that, but go and see the recap of Samson's talk from yesterday, and it will eventually be on YouTube. But the idea of this was that we were funded by DCMS, which is the Government Department for Culture, Media and Sport, in order to collaborate with other institutions on proof of concept projects. Now, this can be related to digitization, biodiversity monitoring, species trafficking, things like that. Now, the project that I'm going to be talking about is related to herbarium sheets, and it was in collaboration with Royal Botanic Garden, Edinburgh. So Royal Botanic Garden Edinburgh, RBGE, is a massive institute where there are 400 million herbarium sheets. Sorry, there are 3 million herbarium sheets, not 400 million. And over 1 million of those have already been digitized, which is fantastic. So I'm just going to go to the next page. Did I skip the page? Okay, no. So this project relates to that sort of digitization. So digitizing a specimen is one thing, but what if the digitization didn't go well? Then we may have some problems. It's estimated that the cost of redigitization is about £1 per specimen, which might not sound a lot, but when you add up the amount of herbarium sheets out there, that can be a lot. That's something in the thousands, and also something that takes a lot of time to do as well, especially if this was a collection that's been hidden away. So our project was on looking at what we can do with AI to make quality assurance or quality control more efficient, so we can spot these before it's too late. So there's 2 things we're thinking about here. If I can go to the next page. Okay. So when someone is digitizing a specimen, can they see there and then where if something was missed, if it's been a good digitized specimen? And secondly, what about the things that we've already digitized? Can we take a sample of those and see if you're doing batch processing, see if there's any that may have caused issues? This could be a camera issue, it could be a person issue, it could be a computer glitch. We're not blaming anyone, it could be absolutely anything. So our project is all about that. So it's all about using AI for this. Now, before I go on about how we did things, so most importantly, here is the team. So you may have already seen some of us here. So the main data scientist on this project was Mei-Feng Zhang, who is no longer with us at the Natural History Museum, but there is an arrow pointing to him. Yes, hopefully you can see that. And then myself from NHM, Samson Poon and Ben Hartley here. And then from RBGE, we had a fantastic group as well. So Elspeth Hassan is somewhere in the room. She is, I can see her. Also, and some others from RBG as well. So Robin Drinkwater, Melanie Phillips, and Rob Keeley. And this is a fantastic photo of us pretending that we're doing work, pretty much just posing for a photo. Okay, the key steps. So the key steps here, firstly, identifying the problems. So there's a lot of problems that you can come up with, but we might not want to include all problems necessarily. This could be something that's very, very specific to RBGE, for example, or it could be something that you may have just seen once or twice, and there's no point trying to create an AI algorithm for something like that. So that is the main step. Now, the biggest and probably one of the most important steps is the curation of the data set. So this is a data set not just of bad digitized sheets, but also really good ones as well, because we need that comparison. So we had the folks at RBGE do a fantastic job at curating this data set for us to work with. It did range from a couple hundred for a specimen for an issue to just under 10 for certain issues. But overall, we had over, I think, around 1,000 images, correct me if I'm wrong, of herbarium sheets for this. Now, bear in mind, this was a proof of concept 3-month project. Of course, if we want to be rolling this out, we will be doing tests from bigger samples, but I will get to that later. Okay, and then the next step is the AI side. So how can we use AI? And I don't just mean deep learning AI, but I also mean classical machine learning tools as well, even just computer vision related things as well. And next, we also developed a pilot app for this. So it's a pilot software. And the idea for this was for if you're doing in situ digitization, if someone is digitizing a herbarium sheet, can we have another screen showing the software and telling what's missing and what's wrong? And then lastly, it's all about gaining feedback from the actual digitizers. So rolling this out to folks at RBGE and testing how it's been working. Okay, so here's some example problems here. So how well can you see this? Okay, not too well. Things like computer glitches, bars on herbarium sheets. This is nothing to blame with the digitizer. It's just a computer glitch that's happened. But the more common ones are things like undercropping and overcropping. So by that, I mean if something's been cropped too much. So if you see in the first example, you might not be able to see the full barcode at the bottom because that's been cropped too much. But in the middle example, it's not been cropped enough. There's too much space around it. Other issues include things like missing elements. If you're missing a barcode, missing a color code, color bar, missing a ruler, things like that. And there were some other issues that we briefly talked about, but we decided not to include. So this includes body parts in images. So if the digitizer may have moved too quickly, they may have got a hand stuck in there in the image as well. So we didn't include that one in the end, but we did include those other ones. And an important one to talk about is camera focus as well. So has the camera been focused well? Or maybe you're even seeing issues with the camera that you didn't notice until you look at it months later. And that was not so easy to see on the screen there. Okay, how do we tackle this? So there's I've written 3 here as an example. So one examples would be things like object detection. So going back to computer vision related things like and also deep learning, is this object in your image? Another thing we looked at is on the mathematical side. So things like Laplacian filters, for example, can measure blurriness. Okay, so object detection. Oh my God, I've got 2 minutes left. Excellent. Okay, so this will be speedy, guys. So object detection. So this is very useful for multiple different things. If we can find things like the color card and ruler and barcode and also the specimen, this is good not just for looking at missing objects like missing barcodes, but it's also used for finding out if something was undercropped or overcropped, because we can use those things that are found and create some sort of average, compute averages of ratios as well. So we can see what's the average barcode ratio, the ruler ratio, and the color card ratio, and use that to determine whether things were undercropped or overcropped. So this works well with overcropping, because if we can see only a partial part of the ruler and then compare that with the average, partial part of barcode, and compare that with the average barcode size, we can see that it's not worked so well. So there is a risk with doing things with one object. We do look at multiple objects. So we do look at things like the ruler, the color card, and the barcode, and the specimen as a whole to compare those averages. Undercropping is a little bit easier. So we just look at all the things that you have found on here, the specimen, and also try and look at the overall size of the picture and compare a ratio with that. Now, measuring blurriness, as I already mentioned, kind of goes back to the mathematics. We've got this thing called Laplacian operators that can measure things like blurriness. Now, what you do from there is you get that forever image, and you can then use a deep learning classifier to create a binary classifier to tell you whether this is blurry or not. Now, because I'm doing a speedy version of this talk, so detecting barcodes, that's another thing that we touched on. There was not that many examples of this. There was no point in going into doing some deep AI related work. It was much easier to use basic computer vision for this problem. So all we did was do some contour extraction here. Can we find those vertical lines or horizontal lines? And if they go from the top to the bottom or this side to this side, then we're assuming that's a glitch. Now, some provisional results worked quite well for us. We got some pretty high scores, but as you know, we did have a very small sample, so do take with a pinch of salt, of course. But this just definitely gave us hope as to how we do eventually expand this project. And this was just a very quick demo of the pilot tool that we created as well. So you can upload an image and you get something like this. So you get true and false, whether it's passed or not, and it will show red if it has not been passed. 10 seconds left, so I'll talk about the next step very quickly. We really liked this project. It gave us a lot of hope, and the results were very, very good from our small sample. And this is definitely something that we can expand to other institutions as well. And hopefully Disco will allow us to do that in the future. So thank you for the whole team, and see you later. Come and ask me questions later, guys.
Thank you, Arana. And we must also have another of my colleague from the Natural History Museum London, Chin Chin Gu, but her talk will be online. So,
hello everyone, I'm Harris from Natural History Museum London. Today I will be giving a talk about AI-driven solutions for optimizing the expansion and storage management of entomology collections. Recently, digitizing natural history collection at scale has brought new logistic and creation challenges. One of them is the physical expansion of storage infrastructure. As part of the DISCO UK program, the Natural History Museum London will undertake a massive digitization project to rehouse approximately 36 million insect specimens around 130,000 collection drawers. This process involves imaging a specimen and attaching a barcode to it, as this must be from topside both from both machines and humans. Consequently, this is an unavoidable expansion in the footprint of the collection. Any estimation of this expansion is impractical scale. Therefore, we initiate this POC project to develop an AI model that automates data capture regarding drawer expansion more quickly and robustly than a manual approach. Here's the workflow we built. Before anything, we need to get data ready from digitisation process and data annotations to prepare data for AI model training and testing. We have 5 different aims. Aim 1 is to develop object detection model to detect bounding boxes for objects within a drawer. Aim 2 is to compute total sums of meta-bounding boxes area within each drawer to estimate the current occupancy. Aim 3 is to identify and estimate spatial expansions of specimens with barcodes, and aim 4 is to calculate average occupancy across all detected unit traits. Aim 5 is to compute expansion areas of unbarcoded specimens. I will go to the models we implemented. In this POC project, we focus on the MHM collector fraction, which covers around 11,000 drawers. That we will digitize it. Generating from this data set, we manually annotated 3 machine learning data sets for AI model training and testing. These 3 data sets include drawer data set, multi-class data set covers specimen drawer. The total labeled instances is around 7,000. A binary class dataset, codataset, which is designed to train the detector to identify barcode and background. The total labeled instance of this dataset is 943. The last one is the full dataset, which identify classes for different size unit codes, including A, B, C, D, E. The total labeled instance is 642. After having the data ready, we can now power occupancy and expansion estimation with object detection. Our object detection is a Euro-based model bridge from raw images to the quantitative inputs. As shown in the label and image examples, our models will detect all different classes, and those bounding boxes are the engine behind all other aims. In the tables, all models obtain very good mean average precision 50, the MAP 50, while MAP can be treated as accuracy in object detection evaluation, and the MAP 50 to 95 column show that our model achieves state-of-the-art performance in real-world application. With high-quality boxes in place, we can now quantify occupancies and project expansions. We introduced 3 different ways to calculate the expansion rate. First, the first method is to calculate expansion rates per drawer by measuring the total area occupied by specimen and their labels. This method ensures overlaps are counted only once using polygon boxes. It preserves creators' arrangement preference, but may actually cause visibility issue due to closely placed specimens. The second method is to calculate the expansion rates by averaging the occupancy areas of barcode attached specimen across the entire dataset. The third one is try to average the expansion rate per specimen using only bounding boxes area. Every specimen contributes equally to the final value regardless of their size. On the right-hand side is the visual representation of the polygon masses, and the left-hand side is the original images. We tested all 3 methods, and now let's look at the output in practice. The patrol rate 1 is around 12%. Is laid out aware and conservative. The global total rate 2 is around 90%, which is like most similar to what our curator expected. And it's simple and best for estate level planning, but it also hides some variability. The pre-specimen rate 3 is around 22%, which captures variation with CIs. Great for analysis, but definitely be more noisier, like for smaller specimen. As both per draw rate 1 and per specimen rate 3 have CI, we did compare the distribution. The rate 1 distribution is tightly rescued, with most draw showing expansion rate below 0.2. This suggests that most draw experience only moderate increase in area. Possible reason could be overlapping. The rate 3 distribution show a biomodel structure. This first pick near 0 is likely because barcodes have no significant increase on large specimen. The second pick is around 0.3, suggesting barcode additions has noticeable increasement on a large number of smaller specimen. This finding actually indicates that specimen level impact are quite huge, and the total draw expansion remains more moderate, particularly for smaller items. Therefore, while rate 1 and rate 3 provide a micro role, rate 2 is rated as a total base average expansion rate given a macro rate of expansion estimation. After all statistical analysis, we projected our POC findings to the whole entomology collection, and the result is shown in the tables. Beyond storage estimation and budget planning, every module in our workflow is flexible and can be plugged into our day-to-day digitization creations. For examples, tracking missing barcodes, tracking relocation, and guiding recreation or rehousing process. To make this reusable at scale, we are happy to release the code openly, and we will keep improving the workflow in the future. Thank you for listening and happy for any questions.
Okay, so thank you to Hirsch for that talk. I'm not sure if she's online for questions, but we'll do those at the end. And next we have another recorded talk, and that's from Ahmed Mohim, who joins us from the Higher School of Computer Science and Digital Technology in Algeria.
Good morning, ladies and gentlemen. My name is Ahmed Mohim, a computer science engineer from Algeria. I studied at the Higher School of Technology and Computer Science in Bijaya, Algeria, and today I'm pleased to present our work on fine-tuning language model for exploring herbarium images through question-answering approach focused on plant traits. This project was carried out in close collaboration with my colleague and friend Anis Soukid as a part of our final year engineer internship at the French Research Institute for Sustainable Development (IRD) within the UNESCO under the supervision of Dr. Youssef Seklab. This work was also carried out as a part of the EcoPlus project led by the National Museum of Natural History in Paris within Work Package 4. The project aims to develop an artificial intelligence system capable of automatically annotating natural history collections in order to enrich with metadata and thereby enhance tools for data-automated research across these collections, which often comprise millions of specimens. In this study, we focus specifically on herbarium collection. To start, herbarium collection are scientific treasures, some dating back centuries. Thanks to digitization efforts, millions of specimens are now accessible online. But while the images are available, the associated metadata is often minimal. Species name, collection date, and occasionally location. This is not enough for modern scientists. scientific exploration, where we want to ask more complex questions like which specimens have thorns, which shows reproductive organs. With over 3,000 possible traits, manual annotation is unrealistic. That's why we turn it to AI. We tested several state-of-the-art deep learning models on a dataset of herbarium images, annotated for 28 different botanical traits. These models performed well during training, but their accuracy often dropped when we tested on new and same images. But why? Why is that? Because the model does not truly understand what a plant is, nor where it is located within the image. They often learn from the background, the paper texture, the measurement scales. So when a model gives the right prediction, it's often for the wrong reason. This brings us to our central question. How can we help AI focus on the plant itself? So far, our digital approach has been like hiring two different experts who can't communicate. We have a computer vision, the AI that sees. It can analyze millions of images and identify which one contains, for example, ovate leaves or green stem. Then we have the language AI, the AI that reads. It can scan thousands of pages of botanical text and extract every mention of serrated margin, for example, or logo. But there is a problem. The scene AI doesn't understand what serrated means, and the reading AI cannot actually see the leaf. Each provides valuable information, but they offer an incomplete piece of the same puzzle. What's the missing is the connection, the bridge between vision and language. The breakthrough represented today is a new kind of AI. It's a multimodal system, meaning it learns from both images and text simultaneously. Think of it not as two separate experts, but as one unified intelligence. It learns the visual meaning of the word, for example, lanceolate. It learns to associate the texture it sees on the stem with the word, for example, reduce in a version. For this task, we chose a powerful open source model from Google called Polygemma. Polygemma is a vision language model, means it contains both visual and textual modules designed precisely for this kind of integrated learning. In essence, our goal was to take this powerful general purpose tool and train to become specialized digital botanist, an AI that's capable of looking at specimen and reading its description, understanding both in a coherent. So our training began with a foundation of expert, 4,000 herbarium images annotated for 28 botanical traits. But the AI learns best from conversation, as we know, not just list of facts. So we used an AI to automatically convert those annotations into a massive curriculum of over 50,000 question and answer pairs that a botanist would ask. For example, what is the texture of the stem? Describe the leaf tip, and we gave it an expert answer. This is how we taught our model to think like a digital botanist. But does it really work? Let's see it in action. We started with a standard AI model, asked it to describe the leaves of specimen for it. Its answer was something vague. This plant has several leaves. True, but not helpful. Then we asked our digital botanist the exact same question, using the exact same image. The response was completely different. The leaves are elliptical with a rounded base and a pointed tip. So it doesn't just see, it characterizes. And it doesn't just describe, it identifies. So it speaks the language of botany. Now, this visual example is compelling, But in science, as we all know, we need to quantify this improvement. So we compared our trained digital botanist against two baselines, a standard and trained version of Polygamma and an evolution one. The results were not just an improvement, they were a transformation in semantic understanding presented by the S-Bird and BERT score and its ability to grasp meaning of the botanical terms. Our model scored 40% higher. But even more impressively, in lexical accuracy, presented in blue, rouge, and meteor, its ability to use the exact button it would use. Our model performance jumped by over 200%. The numbers are clear. Generic AI understands the request, but our fine-tuned digital botanist understands the science behind it. It's not just a minor improvement. It's operating in a complete different class. However, like any scientific advancement, it's important to be transparent about the current limitation. Because it's not a magic bullet. Our model's knowledge is currently limited to the plant families and conditions presented in training data. So to truly scale, it needs to see a wider variety of life from across the globe. Furthermore, while our automated metrics are strong and ultimate, the ultimate judge of scientific accuracy stays a human expert. The next crucial step is to validate those results with a expert botanist, to understand the nuances the numbers might miss. This is a powerful proof of concept, but the journey continues. The work of understanding and preserving our plant biodiversity is a collaborative effort. The technology I've shown you today is a tool built to serve this community. I would like to thank all my collaborators and our institutional partners for making this research possible. So let's continue the conversation and work together to unlock the rest of nature. Library.
That was another excellent talk. And now we welcome David Williamson, who is joining us from the Norwegian University of Science and Technology.
Thank you, Nikki. Yes, so today, adjust this. So I will be having a slight change in topic because I will not be talking about generative AI today. I'll be looking at more traditional machine learning. And I hope to convince you that, as people have said already, that this is still useful even in the age of AI. So I think the first two statements here you will not find very controversial. We still don't know enough about the species that exist on the planet, and we don't know enough about how they are changing, how biodiversity is changing due to climate change and other human effects. But perhaps you're not so convinced that museums are the answer to this. There was a talk yesterday where they said most new species are not found in the field, they are found in the laboratory or in museum collections, and museums hold such huge collections that it's really important that we get access to that data, as I think other people have mentioned already. So we want to look at large-scale studies, we want to look at global studies that sort of exploit the data that exists in these collections. And to do that, we need new methods, as I think most of you already know, such as machine learning, such as AI, such as automation to get through the vast number of specimens that we have. So I want to talk about herbarium specimens. The talks today have already been about this. I think you're familiar with what a herbarium specimen is. And thanks to the great work of people at Kew, at NHM, at hundreds of other herbaria across the planet, we have more than 400 million herbarium specimens in collections. And GBIF contains just over half of those as far as we know. At least it contains records pointing at just over half of those. And so here are some examples. And you can see a distribution map of where GBIF herbarium specimens can be found. You can see there's a bit of a bias perhaps to the distribution. We'll come back to that perhaps. And so we thought, okay, this is great. We can do a really big study looking at herbarium specimens, looking at the phenology, so how the seasonality of flowering, for instance, changes or has changed over time, looking back several hundred years. And that's exactly what we did. We took more than 10 million images. That's a bit less than the 250 million that I just talked about. I'll get to why. And we looked at global vascular plant phenology, and we found some changes. So you can see on the left here is the distribution of where we got images from. Again, there's quite a bias. You can see the Americas and Europe are quite well represented, but then Africa, Asia, quite less represented. And what we found overall is that almost everywhere in the world, the phenology of flowering plants has changed. They are flowering either earlier or later in the year than they were previously. And this change can be seen since the Industrial Revolution, but also since the 1970s, when we can say that perhaps climate change has sped up or is more noticeable. And some plots here, I won't go into these in detail. We have a paper out that you can look at to see more of this, but essentially we found that in the tropics, there was more change than in sort of more extreme latitudes, which we were not so much expecting. And here's some examples from very close to where we are now. So you can see here 3 different WWF ecoregions, the Magdalena Valley montane forests, some Paramo and some other montane forests. And these graphs are meant to illustrate how the seasonality has changed. So along the x-axis is the day of the year. So starting on the left is January through to December, and on the y-axis is the likelihood that the plants were in flower according to our model. So this is all plant species that have flowers. We aggregated everything together, and we can see that there has been quite some shift between about the 1890s, early 1900s, and 2010s when these data come from. And it's a little bit hard to explain why this is. You can see that perhaps the seasonality has shifted, but also that the likelihood of plants being in flower overall has often declined. And there are more than 800 ecoregions. Some of them are very sparsely sampled, so it's possible this is data artifacts from the sampling, artifacts in the model. Our model had about 85% binary accuracy, which we thought was quite good, but there's still some scope there for error. But yeah, overall the message is sort of, phenology is changing, and we will do more work on this, where we will go into sort of more restricted taxa and more restricted geographic regions to kind of dive into that a bit more, figure out what is the exact connection with climate change too. But some sort of early results there from our first, I guess you can call it a pilot study, looking at the entire planet. But there are some challenges in this, and I think this is important to talk about. There are these 250 million records in GBIF, but only about a quarter of those actually have images associated with them, and just over half also have the date, and then about half of those also have a location. And you really need date and location for this kind of study, and I think for most kind of studies that people would like to do with this kind of work. And then beyond that, we also have problems where the species are not identified very specifically, maybe only to the order or to the family level. Quite a lot of the images we tried to download, we found that they were not available, perhaps because the servers are down or the link is broken. I spoke to quite a few herbaria to the follow-up study that we're doing now, which focuses on the northern hemisphere mainly, and many told me that they are being well, not attacked, but you can call it an attack by sort of AI image scrapers, where they're trying to just get lots and lots of training data, and so they're restricting access to their collections as well. So there are some problems here. And this also goes beyond GBIF. We are not just looking at GBIF in the new collection, we're looking at other collections elsewhere, since GBIF is unfortunately not quite yet a global database. So that's one study, but I'd like to talk about another study that we are in progress with at the moment, and I have to thank Professor Meyer this morning because he set me up very nicely for this one. We're going to talk about dark taxa. And so you know already from this morning's plenary session what dark taxa are, and I think if you were quick, you even saw that Megacelia were mentioned in Professor Meyer's talk. So it's a very large, very diverse genus, and it's very poorly understood. We don't really know we suspect that 90% plus of these species are completely unknown so far. And it's important to look at her museum collections that we already have, because those contain a lot of useful information. They contain, type specimens, but often they have been stored in such a way that it's no longer possible to get molecular data out of them. And so we'd like to connect museum collections where these important specimens are to, for example, Malaise trap specimens, which are newly collected, which we can do molecular analysis on, but also we want to do exactly what Professor Meyer talked about this morning. We want to automatically ID new specimens coming from Malaise traps so that we can rapidly identify new species and understand more about the biodiversity of this genus as a sort of proxy for biodiversity overall. And so briefly, we have this very important collection in Cambridge in the UK. It looks like this in these boxes, and these boxes contain hundreds of trays, and each tray contains dozens of slides. And from these slides, we are looking at the wings specifically. So we're taking photos of the wings using a microscopy setup, and then we are landmarking the wings, and we're using these landmarks to produce a sort of shape metric, which you can use to compare different species and different specimens within species too, of course. And you can see here some very early results that we have where the different colors in this plot represent different species, and you can hopefully see that there is some kind of clustering. We need to do a bit more analysis to actually be able to reliably identify species, but this method we think will work, that we can start to get new species from Malaise traps, compare them against our collection here, which we're still digitizing. It's a huge collection of many thousands of slides, and hopefully that will be really useful in the future. But again, there are some issues, and slides are not super easy necessarily to digitize. You've heard a lot today about trying to extract information from notes, and again we have the same problems. The handwriting can be difficult. You think OCR is easy, but there are still some pitfalls. The slides degrade over time. Many of these are decades old, and the slides are not at all standardized, so the metadata you want isn't necessarily on the slide at all. You probably don't know, is this a location down here? This actually is. This is an old UK OS coordinates. You can see RHLD. This is Dr. Disney, who collected this slide. But none of this is very obvious, and it's especially not obvious if you're not an expert working with this collection for many years. So I think most of this we've already heard today. You already know about it. But I do want to highlight the second bit here. For exactly this kind of reason, you still need specialist knowledge when you're doing this kind of digitization work. You need to know what to digitize. You need to know what you want to find out from the digitization. And you need to have some knowledge of the domain to really do effective digitization. I also want to mention that, metadata standards are difficult. But also specimens are often were not collected with digitization in mind, we're not collected with machine learning in mind. So as Rudolf mentioned this morning, we have to think about this and sort of think about digitally native specimens in the future when we're collecting them. Can we make sure they will be suitable for machine accessibility? I think I'll skip this. I did want to talk about more, but someone preempted me with a very good paper, so I recommend if you're interested in digitization, you read this paper here. I won't talk about it further. And final thoughts, yes, this is urgent. Yes, we need to be fair, and we also need to be machine accessible. And I didn't talk about this so much, but it's important that we have input from scientists when we're creating these models, as I think you've already know and have been talking about today. And very crucially, we still need expert domain knowledge as input here. And on that note, here are some of the experts who were involved in these studies. They have the domain knowledge. I'm just the computer scientist. So thank you very much to all of them. I think these slides will be available online later, so if you want to do some further reading, it's here too. Thank you very much.
Okay, so next we have another in-person talk. Can I welcome Majid Rafadar from Museum of Natural History, Berlin.
Buenos dias. Hi everyone. I'm Majid Rafadar. I'm a data architect at Museum für Naturkunde Berlin, or Natural History Museum Berlin. And I'm honored to share my work here with you guys. So I have developed a centralized service for automated data integration in our museum, which I hope that would be a good solution for accelerating the data integration and make it available internationally. First off, starting with some definition. So data migration is more or less a project that you permanently move or copy data from one place to another, while data integration is a permanent process in which you can apply multiple data migration. There is a methodology in the industry to actually apply data migration and data integration. One of them are called ETL, which stands for extract, transform, and load. So data will be extracted from different sources. They would be transformed according to the target system that they are going to be loaded later, and then they will be loaded in these target systems. The concept is very simple. So in the context of our museum, we might extract data from different collections like inventory and so on, or digitization pipelines, or some legacy data here and there, and we would like to transform them to comply with data standards and also to comply with the destination of those data, which would be the target systems we have. For example, in our museum, we have collection management system specified. We also have digital catalog as a media repository and to access the media of our collection objects. And as a final destination, of course, GBIF. And there are also third parties involved that needs to collaborate with our data. So you can imagine this data transformation can take place in one place that is designated for data transformation, and at the same time it has the enough computational power to do those kind of tasks. So here in the left side you see those sources that are permanently connected with the app that I have developed, Data Hub, and it might be connected through different protocols. And on the right hand side you see the target system, so to call, and these are also connected through API endpoints of those target systems. So simply you can see that there would be pipeline here that would permanently be in place to help us to apply these data integration in a more smoother flow. And there is also an AI agent that I have developed recently to also facilitate the execution and optimization of these data integration pipelines, which I explain a bit later. And also, I have to also mention that those services in the right side, they actually could be also sources of data in which we extract data again from them. For example, we have our collection management system specify that we might extract data from that, so to prepare it, for example, to transform it to Darwin Core Archive and prepare it for GBIF. There have been many features that has been developed in the last years on Data Hub. So it's a web app based on a Django framework that can run custom Python scripts. You can deploy it on the cloud or locally. You have a machine-readable interface to communicate with this service, and also an MCP layer that makes it AI-readable, which I explain a bit later. You can apply different data transactions between different services, data transformation between different data types and structures and standards for archiving, for example, quality assurance for dataset validation and delivery, and quality control for object, media, and metadata. And performance-wise, you can actually see live reports easily, and you can run this you can run as many tasks in parallel as much as your computational power let you. And of course, it would be scalable and at the same time considers the constraints of the services involved in the data pipeline to avoid overheads. It has a simple user interface, so our digitization manager and data managers can also log in through an authentication and authorization layer to access their own data, and they can use different filters to manage their data and also make reports or also executing different data integration tasks. So I want to focus a little bit more about the AI feature that I have developed recently, and what I have mentioned before, it's an MCP layer. So I was wondering if any of you heard about this tech layer before. Maybe you raise your hand. Yeah, thank you very much. So it actually makes your application to access to an LLM or an AI agent in a way that these AI agents can easily run different tasks on your website, calling the APIs of the system that you have developed. And it can be easily deployed on any services, any software that you have. I have used LangChain as a framework for developing LLM models, so to test this MCP, and also I've used AI agent QN3 that had the best benchmark dealing with MCPs so far, and it is running on the Olama that is running locally on the machine. So putting it all together, so you can see on the behind me actually, we have a data hub that has an API layer and also an MCP server. And on the right side you have the LangChain that actually enables the model to communicate with this MCP server to an MCP client, so-called. So in this way, any kind of AI model can communicate with your service. So here I have Data Hub, but you can replace it with any software here. As long as it has MCP server, it makes it compliant with many AI models. So as a use case, I have to say that in the last 4 years, Data Hub have been used in many projects in our museum, from mobile data integration to mass digitization. I'm talking about data integration of hundreds of terabytes of data and images. We also used some machine learning to rotate the images that we have based on the orientation of the text in the images, which was also we used Data Hub for this purpose, and also we can use this for some data enrichment on taxonomy and so on using international databases. These are some references to the technology stack I have been using. And before I finish, I have to say that, so I have developed this more or less alone in the last 4 years, but of course with collaboration of many colleagues in our collection and digitization. And there is a public demo version of the source code available in our GitHub. You can scan the QR code to get there, and well, there are enough documentation for you to start if you want to also deploy it on your computer or your institute. This is MFN Data Hub, but it can be your institute Data Hub. So we are seeking for collaboration, and I would appreciate if you, sign in. Thank you very much, and yeah, I truly appreciate the opportunity from the organizers, and thank you for your attention. Have a good day.
Okay, thank you very much. And next we have Chandra Earl from the National Ecological Observatory Network.
Oh boy, okay. Hi everyone, my name is Chandra Earl. So as was just recently said, I work for the National Ecological Observatory Network, or NEON. So today I'm going to talk about integrating digitization and AI for multi-specimen imaging and downstream research. This is a current project that we have in collaboration with the Imagomics Institute out of Ohio State, where we're currently working together on new approaches for large-scale specimen imaging within our collections. So first, a little context about NEON. So NEON is a long-term ecological monitoring observatory distributed across the United States, including Alaska, Hawaii, and Puerto Rico. So we are a research platform for discovering and understanding specifically the impacts of ecological changes, and we do this by gathering long-term environmental data. We have 81 field sites representing 20 ecoclimatic domains, and we provide a highly coordinated system of open data for monitoring over 180 data products. And so the intent is to collect these data for 30 years, with the observatory becoming fully operational in 2019. So we've been in full swing for about 6 years now. Most specimens and samples collected in the field are sent to the NEON Biorepository, which is physically located in Tempe, Arizona, at Arizona State University. We accession over 100,000 specimens per year across 65 different sample types. So here's a list of some of the things that we accession from the NEON project, but this talk is specifically talking about the ground beetles. Currently, we have a little over 83,000 specimens in our collection, and so now all of these have been digitized primary data. But before this project, there was very little of the collection that had actually been imaged. So as you can see, our collections are placed into cabinets, pretty typical of natural history collections, into trays that generally organize these, generally organize the beetles by their species and location. And so instead of focusing on imaging individual beetles one by one, which would of course be incredibly time consuming, we decided to look at imaging that entire tray. So it almost feels like I'm jumping ahead a little bit straight to the results, but here's what those trays end up looking like once they are imaged. And as you can see, our trays are imaged in a very standardized way, with things like lighting, zoom, color, and size standards the same across each image. So the standardization was driven by a set of considerations that were developed to make these images suitable for downstream computer vision tasks. And so David showed this in his slides, but I get to talk about it a little more. So this slide shows the framework that we use to guide our imaging workflow, which was specifically designed for capturing images for computer vision-powered taxonomic identification and trait recognition from specimens. So the considerations are, of course, grouped into two categories. So in blue, you sort of see the factors relating to optimizing the image process itself. So things like specimen positioning, calibration for size and color, handling lighting and shadows, background, and ensuring enough resolution and magnification to capture important details. And in orange are the factors related to data quality and usability. So making sure the images are consistently linked to metadata, that file formats and storages are standards, and the data can be archived and shared in ways that keep it accessible and useful for downstream application. So this paper was led by Allison East out of the University of Maine, and of course this paper is available on the QR code in case anybody is interested in reading that. So in the individual beetle trays, the beetles are ordered by sequential ID number. So that means since all of our beetles have that associated digital data already, we should generally know which beetle belongs in each tray, and if they're ordered correctly, we should be able to determine which beetle has which ID number. So again, in partnership with Imagenomics, they developed a segmentation pipeline for these trays to use an image detector to detect individual beetles in each tray. So if this all works correctly, we have something like this, where each beetle is segmented out as designated by the red boxes surrounding each specimen. However, as we know, pinning is not a perfect art, and that results sometimes in misdetections. So for example, here are two issues with the heads of the beetles. So the one on the right, we can see that the head itself has fallen off and it has segmented that head out on its own. And on the one on the left, you can see that this head is just really big, and so it decided to segment that out, its head out. We also have some examples of beetles that are placed in pin tubes, which don't get segmented out correctly either. And this is sort of just the overview of the final segmentation pipeline, which included validation on the images. So basically the way this works is that the image detection is run at a certain threshold value, which essentially represents how lax or how strict that object detection is. And we see if there are any detections made. If yes, we take that detection area and white it out, which results in the image that looks like something like this on the right. We run object detection again. Of course, the first time it runs at that same threshold, so there's going to be no new detections. And so we decrease that threshold and sort of try again. So now we do have to set a minimum threshold value, or what happens is something like this, where the detections become too lax and just ultimately incorrect. So after we've hit that minimum threshold value, we give we give the photo with the whited out beetles images to an LLM, and we ask it, hey, are there any beetles in this image? If it doesn't detect any beetles, it passes our segmentation pipeline, and we assume that all beetles can be segmented out using the number of segmented beetles. That we also do have some kind of validation there, because we do know how many specimens should be in that tray from the data, and we know from the metadata, from the imagers, we have the imagers actually count the number of beetles that are in this tray. So if all those numbers match up correctly, then we can be fairly confident that the segmentation has actually worked. So far we have imaged 3,500 trays, so that results in about 56,000 specimen images. So this means in about 4 months we've imaged 67% of our beetle collection, and we are able to link all of these images to the associated NEON data due to how the beetles are pinned. So not only have our beetles been imaged, however, but we've been able to image them specifically in a way that is designed for computer vision analysis. So that means we can do a few cool things with these images. So for example, we can use segmentation layers to isolate body parts and automatically collect some morphometrics. So it's not as precise as manual work, of course, but it lets us generate some trait ranges across those 56,000 specimens very quickly. And so with that much data, we can begin to ask questions about things like trait evolution, species level thresholds, and functional traits. And then because these specimens are specifically from the NEON project, we have rich environmental variables to pair with those traits, which opens the door for large-scale comparative analyses. So for example, here are some of those data. So I've pulled the ones that are the most relevant, and at least in the context of ground beetles. And so the point here is that the potential applications here are very broad, and I'm really excited to get sort of these traits into our database for people to use. So using the beetle image data set that was created, we actually currently have a published machine learning challenge where we are trying to challenge folks to create machine learning models to see if they can predict drop status from the collection time of the beetle from the beetle images themselves. So for example, we've made available the individual beetle images along with some collection metadata and the standardized precipitation evapotranspiration index, or SPEI, which was calculated at 3 time windows before that beetle's collection: 30 days, 1 year, and 2 years. So the challenge is currently open and available on Codabench if you would like to make an attempt at this. The team with the best results against our testing data will win $4,000, yay. And the challenge closes on January 31st. So again, here's the QR code in case any of you are interested in attempting that as well. And of course, this was not a small effort. Rather, there is a whole team of people who have had some hand in creating this data set. And of course, if you have any questions, feel free to contact me or find me after this. Thanks.
Thank you. And our final talk today is by David Wolnick, who joins us from McGill University in Canada.
Testing. I'm scared of the slide control here. Everybody's been having slide problems. Oh dear. Thank you so much for having me. It's a pleasure to be here. I'm going to be talking about insect monitoring. And to start out, I don't think that this audience needs much motivation for why insect monitoring is important. You can see on the left-hand side here the comparative diversity of different animal groups. Insects dominates everything. Half of all described species of organism overall are insects, and there are a lot more that are undescribed, as we've heard several times today. On the right-hand side, you can see, however, the difference in IUCN assessment status across different groups, and there are most of the mammals, most of the birds that have been assessed, and most of the insects have not even been assessed. Now, of course, the quality of assessments can differ, but the vast majority of invertebrates overall have not got very much data associated with them at all. And this is a massive problem, if for no other reason than that insects are disappearing worldwide. People talk about an insect apocalypse. Different studies in different places have seen dramatic plunges in insect numbers, which have been attributed to everything from land use changes to pesticides to climate change and combinations of those different factors. And perhaps the scariest part about this for me is that this is often called the windshield phenomenon. We have so little data on insect populations that sometimes the best way we can work out that vast numbers of insects have disappeared is by noticing that we aren't hitting as many with our cars. This is terrifying. Now, we're trying to attack the problem of data availability for insects using camera traps. There are a range of options which are increasingly being built by some of our partners, the UK Centre for Ecology and Hydrology, Outreach Robotics, and the Mothbox. Mothbox, I should note, is actually open source. These are some of the many different solutions which are being built on the hardware side for camera trapping insects. These all have some kind of UV light which will attract nocturnal insects. Best way to get a large number of insects to a single place, a white sheet that they come to, and a camera which will take photographs automatically. Now, we're computer scientists. We work on the other part of that, which is processing the data coming in from these. And the data can look like this. This has some notable features. First of all, massive amounts of it. Not just massive amounts of images, but massive numbers of insects on a single image, right? And that is massive numbers of species as well. So there could be, even in a relatively non-biodiverse region like Quebec, where we are, there could be thousands of species of moths present in a particular location. And most moths, most of the species that we're going to be looking at are moths, because that's the bulk of the images, bulk of the insects that come to nocturnal camera traps, but also they can be visually identified, often to species and at least a genus. So there is a huge opportunity for computer vision in monitoring all of these insects, actually non-invasively, they're not even being killed, but really doing this scalably. And should note, these are different challenges from standard camera traps and from algorithms with standard camera traps, where you might be used to a large mammal coming by your camera trap very occasionally. So the data is kind of There's a lot of it, but it's sparse when you actually get an animal. Here, you've got all the animals all the time. You've got hundreds of moths. They're sitting on top of each other. It's really hard to work with this data using the same kinds of algorithms. You have to design new ones. And this is what you'd really like to have. This is from our algorithmic pipeline, spoiler. But what you would like to have is you'd like to have all these nicely little segmented moths with species and numbers showing how confident you are in that species, right? You like some other things as well, which we'll get to too. This is our pipeline for the AI systems. We're taking a raw trap image, detecting particular insects, and then we're focusing primarily on moths. So we have a classifier for moths and non-moths. We can also classify different orders. So if you're interested in Trichoptera, we can pick up the Trichoptera, for example. And then fine-grained classification of individual moth species, and then tracking to see how many individuals there are. Like if it's the same species, it's the same individual, just not moving very much across images. That's very helpful to know, for example, for counting. Now, the algorithms here are being trained from GBIF index sources like INAT. That's partly so that it can work with different traps. All that diversity of hardware. You'd like a system that will work for any of that hardware. So we've got a system that will work for any of that hardware. You can fine-tune it using the data from your particular trap, of course. Now, we use data augmentation, given that the data is different. It's coming from citizen science, and it's coming from museum collections. It's not going to look exactly the same as camera traps, but it's actually good. The camera traps are generally against a white background. They're actually easier images, often, than the images coming in from GBIF. And we can do some data augmentation to account for like the graininess of images with small moths. We can predict at higher taxonomic levels if the confidence is too low, and in general, we find that the species level ID is really accurate when the confidence is high. You can find more details in some of the methods we used and some numbers that paper. Their algorithms have actually even gotten better since then. But of course, it's not enough to just have algorithms, right? People can't use algorithms very readily, so we've built a software system that makes it possible to use these kinds of algorithms and do data management at scale for insect camera traps. This is the antenna platform, which is completely open source. You can check it out at insectai.org, and this is the kind of thing that you can do with antenna. You can pick out your insects. In this case, we're focusing on moths, but it will pick out the other insects as well. And you can process very large amounts of data. Here, coming from 63 stations, about 500,000 particular captures. It's finding 80,000 occurrences of moths, identifying them to species. You can go through those and confirm which ones are correct, disagree with the AI algorithms, and provide validation for them, which you can use to make them better. The algorithms that we're using are publicly available. You can use your own as well. And the goal is for this to be a single-stop shop for a lot of different things that you might want to do. You can also do various kinds of data analysis, like work out when the moths are coming to your traps, look at the different kinds of data being picked up by the different traps, look at the top species encountered, etc. The system is being used by a large number of partners across the world, and it's already been scaled up to just a really massive number of images. I want to talk about some of the challenges in the remaining 2 minutes that we encounter in some of those deployments. And in particular, I want to talk about the next frontier, species with no data. This is an example image from one of our deployments in Mount Totuma's cloud forest in Panama, which is incredibly biodiverse region for Lepidoptera especially. One of the things we ran into is that the species which are known there, even if they are recorded, they are not necessarily recorded in GBIF with images. That can be a huge problem if you have literally no training data anywhere in the world that is digitized, and maybe just one image in a collection somewhere that, even if you were to actually be looking at physical specimens, maybe there are only a couple of those. There are a lot of moths which are not present in the right checklist. They haven't been found in the particular place yet, right? That could be because species haven't been found in a particular place, or because the ranges are changing. Invasive species. That could be a reason why you have a species with no data for the particular algorithm that you trained, right? Like you didn't expect it to be there. But then the kicker is undescribed species, of course. We've been hearing about this throughout. throughout the conference, and in particular Dr. Maya this morning, moths aren't exactly dark taxa according to his definition. About 50% of them are described. So in this place, Mount Totumas, we found about 50% of the moths are new to science. Here are some moths from, this is actually Barro Colorado Island, which is one of the best studied locations in the Neotropics. About 25% of moths we are finding seem to be new to science. There are a lot of those out there. So we are developing algorithms that can deal with this problem. We're trying to test classifiers on species outside their training data. And this is an area of machine learning called open set recognition. We're trying to flag what is new to the algorithm. Obviously, you can't come up with a species name if there is no species name, but trying to detect when something is new. And so we're testing this on moths within and outside the region. So you can see, you're testing from a classifier that was trained on Panama. What does it do when it's seeing a moth from outside of that region? And looking at different hops away in the taxonomical hierarchies, like if you're looking at a moth in the same genus, is it able to distinguish that? It's easier if you're looking at a moth that's in a completely new family, for example. And we find that none of the existing algorithms is wholly reliable. We're designing our own, but the just thresholding confidence scores, so the numbers, the raw numbers coming out of the classifier, actually works pretty well as a stopgap measure. That is a reasonable approach to try. And we're testing integration into Antenna now. So if you're interested in exploring Antenna, I encourage you to check out the info and demos at insectai.org. There's a sign-up list for prospective users. Please email us if you are planning a monitoring program or study. This is a beta version, so we are letting people in off the list based upon needs and capacity. And please give us input as well. It's an open source platform. You can check out the GitHub code there. I want to thank all of the amazing people who made Antenna possible. These are some of the people leading the team. And thank all our partners across these different institutions, and also thank the Global Center on AI and Biodiversity Change, which this is a part of. It's a multi-university center across the US and Canada, primarily thanks to the US NSF and Canadian NSERC. So thank you very much for listening, and I look forward to talking with some of you afterwards.
So thank you to everyone who's spoken. Could I invite the speakers to come up to the front so that we can do questions? We have a mic we can take around. Oh, sorry. Take it around. Yep. Okay. Who has a question? Great. Okay, so we've got one from Tanya. One from Tanya.
Great collection of talks, and it's very clear that there is a lot of overlapping tasks, approaches, potential data sharing and data intersections, or kind of one feeding into another. How do we, this is a great group, especially if we focus on the botanical side of things, on the plants, but even beyond. How do we make these kinds of tools and data applicable across, usable across, so that we don't have to reinvent the wheel every single time? And how do we make the data then ready for these tools to be used, so that the process, the human investment can actually build on the other investments that already been made, especially for smaller institutions, for smaller under-resourced places.
Hello. Yeah, that's a great question. I mean, one obvious answer is obviously talking to each other and having that community. But I also think doing things a little bit differently. So maybe if you've got a project idea, not going ahead and making it into a massive project at first, but doing a smaller proof of concept project first to test out how it's going, and then talking to other institutions and other people to come together to create the bigger thing essentially, instead of spending a year working on a project that someone else has also worked on simultaneously. Work on it in smaller projects, sub-projects first, and then expand that in a more collaborative way, I would say.
I can add to that, I think bite-sized pieces. If one is building something big, try to dissect it into small things that can be interoperable.
Yeah, I think both of those are good points, but I'd also add as well that infrastructure can help model zoos, places where we can share some of these, our models, our code, and make them more discoverable. Because yeah, some of these projects are highly relevant and ones that I wasn't aware of until we ran this session.
Hi, I have a question sort of, it'll go somewhere with, primarily especially with Purian and Ben. So my name is Britt Anderman, and I'm working at the Museum of Evolution in Uppsala, working with archival materials and mobilizing biodiversity data from them. And so kind of piggybacking off of what you just said, I'm seeing like very similar work being done in these various pilot projects of ours, different workflows and so on. And I'm kind of curious about when you were developing your workflows and so on, if you were working sort of just, you know, in isolation, if you had any collaboration with other institutions or others doing similar work. And then kind of, I wanted to suggest that I think it would be really valuable for us doing this stuff if we have some more contact and communication with one another, so we're not developing all of our own separate little things and can know how others are working to inform our work.
Yeah, that's a very good question. And throughout my project, I mean, it was my first project with Q, and I've been working on it on my own with some help from Nikki, Ashley, and a couple other curators at Q. And I think, as a good point, it is important that because with the data that we're handling, they have different formats, different types. So it will be good if we can collaborate together, since the workflow will be quite similar. It's just the way we'll handle the data and how we extract them will be different. So it will be nice if we can look into that further and collaborate.
Yeah, I completely agree. I mean, we did have some collaborations with the projects, but more very ad hoc, having somewhere to share these things. And yeah, let's chat afterwards and try and work together on this in the future.
I think that kind of collaboration space could be something that it would be great if we could roll that into the future for BHL, because it's really showing the potential for BHL. And if you think of us using literature as a source, which all your projects have demonstrated, there's an immense amount of networking that's gone on for using specimens as a data source, and we need the analogue of that for literature too. Yeah. Another question or someone?
Hi, thanks. Many thanks for our talk. Sorry, again, a question for Ben. I found it super cool that you have these Flowpo annotated stuff here. I'm happy to see it here. A bit of an issue with Flowpo is that it was developed as a use case for really data-driven semantic artifact at the end. So some terms in it might be a little bit confusing for humans if they read them. And I see you use it in combination with an LLM. You have probably, so to say, two systems. One an older one, Flowpo, is from around 2014 or so, and a really actual one which tends also to hallucination. What restrictions do you use for quality control? And so do you check by humans or crowdsourcing, or do you have automatic checks that those things don't overlap and lead you into bogus with annotations? That would be my question. And a quick follow-up question, do you make these annotations available in a kind of triple store? Because I would be highly interested to see this data, use it. In particular, what we discussed this morning is this idea of using knowledge graphs as definitions for species in the language. That would be super cool if this would be available. Thanks.
first answer, yeah, FlowPo, we're aware it's quite dated. We have developed our own ontology alongside FlowPo. It's a essentially Anna Claudia and Neil Brummett are the botanists that I've worked with in the Natural History Museum, have gone through and derived like a subset of FlowPo that we use, which have the terms that they're most interested in the species predictions, and those are our main targeted terms. We're writing a paper at the moment, and we will release all of the information, the ontologies we've used, as part of that. I think they are already available on GitHub, so I will share them with you afterwards. But yes, we had experts looking at the FlowPo, comparing it with the ontology used by the Flora of North America, I think, and developed for other projects. And yeah, so we've got like a specialist ontology we're using. Does that answer all your questions? If not, I can chat afterwards. Yeah, so it's checked, or a subset of it's checked by the botanists involved in the project. So to make sure that the LLM is outputting the correct data to the ontologies. Yeah. Thank you.
Okay, so before the next question, I do have a suggestion to avoid me running up and down a lot. So may I invite everyone who have a question, please come to sit down in the second row, then we can just yes. Then I don't have to run all the time. Thank you so much.
Yes, I have a question that basically has been questioned already, but I want to pose it a little bit different. So many presentations in this session and in the conference in general has been about developing tools for specimen digitisation which are already existing. So they are available as open source. We have several tools running the Discord infrastructure. So my question is, why did you still choose to develop your own tools there? Could you not find these tools, or are there other reasons for that?
Was there a tool in particular?
Was there a tool in particular?
Gets voted off the island.
Yeah, right. I think for my one, we've been developing it for about 4 or 5 years. I was aware of other trait extractions from literature models, particularly in Spanish when we started doing the project, but nothing that puts output the data in quite the way that we wanted, or to the level of accuracy we wanted. But yeah, I'm aware there's many other people working in the space. So yeah, it's I think having somewhere that we can sort of surface those and develop and discover them would be useful and help with that.
So I think for us, a lot of it was collaborating with sort of the more computationally focused people than, of course, our own little biology people. So we wanted to have the chance to do that, but B, also because, like, from what I understand, imageomics is very big into early career science and allowing folks to develop those skills so that they can then in turn, enter the workforce. And so, yes, we could have probably, maybe we could have done something where we looked and see what other people are doing, but in doing so, we have a whole swath of now, young career scientists who have this expertise and knowledge, and, that sort of gets into just training this workforce more.
I would also add that we do the same with our projects as well. Whenever we start them, we do first look at programs that are already out there that do the same thing. So for example, for our project, we did test out Leaf Machine first to see how that was working. And of course, with some GPU problems that caused later on, we then moved to doing it ourselves, which was quicker to do in that 1 month that we had to develop it. But we did first test out those other methods.
I just wanted to add, because it relates to the previous question too about smaller groups, because we are a very small group. I'm the only computer scientist in our group, and we did very much rely on previously published methods. We still developed our own models because we have a different target set, different training set, but I think some people in the room here had helped develop the methods that we did end up using, and having those available was really helpful for us as a very sort of resource-constrained group.
So I completely agree with Wouter, and I've said this, I think, in 2 sessions now, so yes, we need to work together as a community. But my question was a little more specific to you, Ben. Again, you're a target. Yes, the 25,000 terms that I extracted from the floor of China and floor of North America, sitting in a repo, almost no one knows they exist. You know, we need to do a little better at that. I need to do better. But, you know, looking at the talk from this morning, the keynote, looking at sort of new, novel ways to speed up how we describe species, and, you know, this data integration piece is essential. And, you know, one of the things I've learned in doing that work is that our descriptions, the way, you would think, like, us taxonomists, we're very detailed, focused people, but we're too detailed. And because of that, writing ontologies for these things, even as humans, is annoying and very difficult. And so my question really is, because I'd like to do this, my question is, can AI, looking across, you know, this huge swath of information that we have, can it tame these ontologies to do better knowledge extraction for us? I hope so, because I really still want to do something with that.
Yes, they definitely can. And we haven't actually used like a model for extracting ontologies from the text, but we are using an LLM for mapping between the ontologies. Because when we first started the project, we were more looking at the your ontology and the Flora of North America ontology, and then towards the end of the project, we started developing, or we started using more FLOPO, and then we're sort of integrating those two ontologies and mapping them across each other. So I think actually developing a process that could generate a model, generate an ontology from those descriptions, would be very useful and definitely something we could look at next, I think. Yeah, let's talk.
So I think we're suffering from the curse and the blessing of being biologists, which is biology is this middle complexity thing where all of the interesting stuff is in all the detail. It's not generalizable in many cases. And I am really tired of writing software that I spend 2 weeks writing and it applies to the one problem I have and doesn't go anywhere else. And so I think some of the reason that we're seeing multiple models being developed is because you look at what's out there, like, no, because a shortcut was taken very reasonably at the beginning. Oh, insects are kind of this size. Okay, got it. I can't use that for trees because they don't fit. But some of the things that we hear about are generally applicable if we can figure out what are the specific pieces that need to be abstracted out that can be plug replaced. So, my book has 3 columns, not 2. You know, things like that. So how do we go about trying to distill the more generalizable parts of all of the work that people are doing and isolate the more specific parts so that we can all work together more productively?
That's such a great question. I certainly don't have an answer to it, but I would start out by saying that I think developing funding mechanisms that enable all of us to be actually building these things via software engineers, not doing it by researchers building code. Like, I'm a machine learning researcher. All the biology researchers in the room, like us machine learning researchers, should not be building the scalable software, because software engineers are good at their job. And it's been hugely important for the antenna platform that this is being built by software engineers. It's not being built by researchers in their spare time. Now, of course, that takes funding, right? And thank you to ABC and our other funding sources for tech transfer. And that's not necessarily scalable to all the things that need to be built. And it's not sustainable for the tools that need to be built and maintained. But I would think that really separating the we need this thing for our use case from we need a thing for the field. And maybe there can be more pitching into pots where 10 groups need something built, and if it were done by us researchers, then we would need 10 different things because they wouldn't be scalable. But if we all pitch into a pot, then we can get like an actual software engineering person or institute that will do these things for all of us. And I think also separating the notion of scale with software from the notion of scale with AI. Because people talk about scale and generality with AI, and that's mostly crap, I say as an AI researcher. Like, but training a new model is kind of cheap, right? Like maybe designing the kind of model. No. Come on, Tanya. Like if you have a small data set and you want to refine your model, you want to refine a model for that, it's expensive, but it's much less expensive than building a whole software platform, right? Fundamentally, the thing that's hard is the infrastructure far more than the AI models. And we don't need a single AI model that will do all the things. We need software that will do many of the things.
Yeah, I agree very much, and I think that what you're asking is quite difficult to have something which is both specific and general. I think that we can look at computer vision models like CNNs, for instance, where these days I think most people probably take a pre-trained model off the shelf and they then fine-tune it or adapt it to their own needs. It's of course possible and very, maybe not cheap, but plausible at least to train your model from scratch if you have enough training data, thanks to the really good software that already exists for that. I think that maybe for LLMs that doesn't quite exist yet, and similarly there's not, okay, Tanya says it does, but perhaps it's not well known at least. But I think that we're not quite at a point where we are with CNNs, for instance, where you can just go and grab a thing and it will probably work, but I see there's some disagreement. We can talk about it after.
Okay. Just to respond to Dean's point and the response that David gave to it. How many people in here are aware of the job title research software engineer? That is embarrassingly small. So yeah, it's the job title that has become well understood in the UK and is now taken off in other parts of the world, particularly the US. So you can write them into your grants. So these are people that sit within a research team. They're specialised at working in the research field, but they're specialised software engineers. And I think that's the answer to some of the problems we're getting where we get fragmentation of projects. So yeah, I'd encourage you to find out about that, and maybe we should have a particular network within biodiversity informatics that would help us use those more. I think we are out of time. Yeah. I can stay around and we can.
Okay, so I assume you still have a lot of questions to ask. I actually do have a lot of questions to ask, but unfortunately we run out of time and I know we are all hungry for lunch. So I think so thank you so much for joining this session. We still have our part 3 session tomorrow after lunch. So yeah, I hope we can still all stay awake for the session 3 after lunch tomorrow, and well, I will see you tomorrow then.